Hi everyone. Excuse me. Hopefully this is the last part or the last session for our chapter 18. Okay, let's see here. Salts of weakly acidic cations and weakly basic anions. If a salt that consists of the cation of a weak base and the anion of a weak acid, the pH of the solution depends on the relative acid strength or base strength of the ions. Let's say ammonium cyanide. So ammonium cyanide is a salt. And first thing that you need to figure out whether it is acidic solution or basic solution creates by putting this in water. You have to break this into its counter ions. So ammonium cyanide is made up of ammonium ions and cyanide ions. So ammonium is the cation of a weak base, ammonia, and cyanide is the anion of a weak acid, HCN. Now when ammonium ion you put it into water, what's going to happen? Ammonium ion will lose a proton and become ammonia, and water will become hydronium ion by taking the hydrogen from ammonium ion. And cyanide, acting as a base, will grab a proton from water, become hydrogen cyanide and OH. Now both of these solutions produce hydronium ions and hydroxide. It cannot be both acidic and basic. It has to choose which one it is going to be. To identify whether the solution is going to be acidic or basic, we need to find out what are the Kb and Ka values of these ammonium ions and cyanide ions. Now here ammonium ion is acting as an acid. So we need to find out the Ka of ammonium ion. Cyanide is a base. So we need to find out what is the Kb value for cyanide. And whichever become more higher number will decide whether the solution is going to be acidic or basic. The reaction that proceeds further to the right determines the pH of the solution. So we need to compare the Ka of ammonium ion with the Kb of cyanide. Remember we learned earlier Ka times Kb equals Kw. Kw is the ionic product of water, dissociation constant for the water, 1 into 10 to the negative 14. So if you know Ka, you can find Kb. If you know Kb, you can find Ka. Now for the Ka of ammonium ions, Kw over Kb of ammonia. Kw 10 to the negative 14, Kb of ammonia, which is the base dissociation constant for the ammonia is 1.76 into 10 to the negative 5. So you can find these numbers from a table. So that gives us the Ka of ammonium ion, this value. Whereas for the Kb of cyanide, again going to be Kw over Kb of HCN. So 10 to the negative 14 over 6.2 into 10 to the negative 10. So this value you can find out from the literature values of hydrogen cyanide Kb. That gives us 1.6 into 10 to the negative 5. Now between these two values, which one is bigger? This is bigger, right? So then the Kb, since Kb of cyanide is greater than Ka of ammonium ion, cyanide is a stronger base than ammonium is an acid. So the solution of ammonium cyanide will be basic because the cyanide, so this one Kb is stronger compared to Ka. So as a result, this equilibrium favors and then the solution will become basic. Okay, so this chart summarizes the acid-base behavior of salts in water. Nature of the ions. Neutral solution would be the result if you have a cation of strong base and anion of strong acid combined to give you a salt. For example, sodium chloride, potassium bromide, barium nitrate. Sodium, potassium, barium, they are all a cation of a strong base. chloride, bromide, nitrate, they all are anion of strong acids. Chloride coming from hydrochloric acid, strong acid, HBr, strong acid, HNO3, strong acid. So the ions, these ions, when they dissociate, they're not going to react with water. So as a result, the pH would be neutral at 7. These ions will produce acidic solution. Cation of weak base like ammonium chloride, ammonium nitrate, methylamine bromide. So this ammonium ion here, all of these, that is a cation of a weak base ammonia. And then it combines with anion of a strong acid, chloride, nitrate, bromide. So the chloride, nitrate, bromide, since they are anion of strong acid, they will not react with water. Only ammonium ion will react. So ammonium ion with water giving you ammonia and hydronium ion, H3O+. So as a result, the pH is going to be less than 7 because it generates hydronium ion, H3O+. Okay. And then if you have small highly charged metal cation and an ion of strong acid like aluminum nitrate, chromium bromide, iron chloride, aluminum, chromium, iron, they all are small highly charged metal cation. Nitrate, bromide, chloride, they are anion of a strong acid. So anion of strong acid, they're not going to react with water. Only these ions, aluminum, chromium, iron, they can form a complex with water. And then it further reacts with water, giving you this complex with 5 water molecule and hydroxide and releasing a hydronium ion. So as a result, this kind of a solution will give you acidic solution since it generates hydronium ion having pH less than 7. A basic solution will be the result if you have a salt made up of cation of strong base and anion of weak acid like potassium nitrite, sodium hypochlorite, sodium carbonate. Here these are all salts, potassium, sodium, that is a cation of strong base. They are not going to react with water. Whereas these ones, nitrite, hypochlorite, carbonate, can react with water. For example, nitrite with water, NO2 minus plus water. This is going to take a hydrogen from water molecule and become HNO2. If one of the water molecules lost from one of the hydrogen will be lost from the water molecule, it would become hydroxide. There's a little typo, so I will correct that. Instead of H3O plus, it has to be hydroxide, OH minus. You see, if the water loses a hydrogen to give to NO2, it becomes HNO2. So then the water has to be hydroxide. So that's why pH is greater than 7, which is a basic solution. And then if you have a cation of weak base or small highly charged metal cation and an ion of weak acid, ammonium chloride, ammonium cyanide, lead acetate. So ammonium ions here, that is a cation of a weak base or small highly charged metal cation, and then these ions, they are anion of weak acids. So the cation anion combination would be cation ammonium ion react with water. So this would become ammonia, NH3. Water going to act as a base. Take a proton from here, ammonia and hydronium ion. Okay. So, and then the in this molecule, so that is how the cation reacts, and the anion ClO2 minus in the presence of water going to form chlorous acid HClO2. So hydrogen will be lost from the water because it's going to give to this chloride anion HClO2. If hydrogen lost from the water molecule, it would become OH minus instead of hydronium. Again, here's this one is a typo. So that need to be OH minus, making it a basic solution. So again, we have to check to see if the Ka of ammonia, Ka cation greater than Kb anion, that would give you a pH less because the hydronium ion would be predominate. But if the Kb, we have to check to see what is the Kb value for this one compared to the Ka. If Kb is greater, so then the pH would be higher than 7, would be basic. Okay. And then if you have a cation of strong base and anion of polyprotic acid, for example, sodium hydrogen phosphate, potassium hydrogen carbonate, sodium hydrogen sulfate. And here again, sodium, potassium, sodium, that is a cation of a strong base. So they are not going to react with water, so we don't worry about that. We're going to look into the anion. If you take the anion from this compound, sodium hydrogen sulfite, HSO3 minus can react with water as so this as the base and this as the acid. If here this is going to act as an acid, it's going to lose this hydrogen, give it to water to form hydronium ion and sulfite anion. If this is the stronger dissociation, Ka greater than Kb, so then the pH would be less than 7. And also anion can act as a base by taking a proton from water. So then HSO3 minus take a proton and become H2SO3 sulfurous acid, and this is not going to be H3O plus. Again, that's a typo. It also need to be hydroxide ion. Okay, it makes sense, right? If you have HSO3 and if you are going to make H2SO3, meaning one of the hydrogens from water will be lost to give it to protonate this molecule. So then it should end up being hydroxide. So then this equilibrium would be the predominant one if Kb, if this process is greater than Ka, which is the anion. Okay, again, if it is a weak acid and a weak base combination like that, we have to check to see whether the Ka or the Kb is stronger, just like the previous example we did. Okay, so the leveling effect. What is the leveling effect? All strong acids and bases are equally strong in water. All strong acids, they dissociate completely to form hydronium ions, and all the strong bases dissociate completely to form hydroxide ions. In the water, the strongest acid possible is hydronium and the strongest base possible is hydroxide. So water exerts a leveling effect on any strong acid or base. Now so far we talk about two types of definitions of acids and bases. So the first one that we learned is Arrhenius acid-base concept. Arrhenius. And in there, acid is something that has hydrogen ions. And then the base is something that has hydroxide ion. That is the Arrhenius acid-base concept. Acid is, it should have hydrogen in it. Base should have a OH in the base. And then we talk about Bronsted-Lowry acid-base definition. Bronsted-Lowry. So there, acid is a proton donor. Acid is a proton donor. And a base is proton acceptor. Okay, and then now we're going to learn about Lewis acid-base definition. What do we do here? Lewis base is any species that donates an electron pair to form a bond. Lewis base. A Lewis acid is any species that accepts an electron pair to form a bond. And in this Lewis acid base definition, we don't talk about protons. We talk about electron pair. Base is something that it has electron pair that can donate. Acid is something that can accept that electron pair. So the Lewis definition views acid-base reactions as the donation and acceptance of an electron pair to form a covalent bond. Okay. So a Lewis base, meaning it has a lone pair, must have a lone pair electron to donate. So any substance that is a Bronsted-Lowry base is also a Lewis base. So if you remember the Bronsted-Lowry concept, we said a base is proton acceptor, right? In order to accept a proton, it need to have a lone pair of electrons. So any substance that is a Bronsted-Lowry base is also a Lewis base. Lewis acid must have a vacant orbital or be able to rearrange its bonds to form one, to accept a lone pair and form a new bond. Many substances that are not Bronsted-Lowry acids are Lewis acids. So the Lewis definition expands the classes of acids. In this example, you can see that the electron deficient molecules can act as Lewis acids. Boron and aluminum are often form electron deficient molecules. And these atoms have an unoccupied p orbital that can accept a pair of electrons. Here you can see BF3, boron trifluoride, is going to be your acid and the base is going to be ammonia with a lone pair. So this guy, base, give its electrons lone pair to boron. So boron has a vacant unoccupied p orbital. It can accept this 2 electrons and form a bond, covalent bond, and we call it as an adduct. So the base is ammonia and then the acid is BF3. And another example for Lewis acid, a metal cations. Cations is something that you had lost electrons, right? So meaning it is electron deficient, it can take electrons from somebody else who is willing to donate. For example, metal cation in the presence of the water, we had seen this example several times. 6 water molecules through the oxygen, lone pairs can bound to metal cation. You see here? So that is considered as a Lewis base and your metal is going to be Lewis acid and form the metal hydrate. And here are some examples. Identify the Lewis acids and Lewis bases in the following reactions. So you have H plus and hydroxide giving you water. So which one do you think is the Lewis acid? Which one is the base? Base is something that you have lone pairs of electrons, and acid is electron deficient. So H plus hydroxide. So if you draw the Lewis structure for hydroxide, it looks like this, right? And you have a water molecule. So the lone pair of oxygen donate to form a bond with hydrogen and form water. So this is going to be a Lewis base and this is going to be your Lewis acid. Okay, and then the chloride plus BCl3. Chloride, if you draw the Lewis structure, it has 4 lone pairs. So the lone pair goes and form a bond with boron. Boron is electron deficient, so you can form a bond chlorine, boron, Cl, Cl, Cl. So which one is the Lewis acid? Lewis acid is BCl3 and then the base is the chloride with lone pairs. And then the next one, you have K plus potassium ions and 6 water molecules. Now which one is the Lewis base here? Who has lone pairs of electrons, potassium or water? Water has lone pairs of electrons, right? And this one being a positively charged, it's electron deficient. So this is the Lewis acid and then water is the Lewis base. Okay. So the explanation is also here. Okay, so that conclude our session for chapter 18. So we learn lots of new chemistry, very interesting. Now you guys can do your homework. There are 2 sets of homework for this chapter too, so you should be able to do those things. So I will talk to you soon. Bye bye.